Hi, this is Adam Cankaya. I'm going to go over the final results of the work I've done over summer 2025 on this bladder cancer paper implementation. What I've particularly done this summer first was to implement this WGCNA. This is the weighted gene coefficient network analysis or co-expression network analysis. The idea is to see which genes can be grouped together based upon their expression being similar. So that basically certain genes are expressed together as a group. And by thinking about them in terms of groups, we can not only simplify the calculations, but also possibly get some insight into the relationships between the genes themselves. So this step 4 is where I've implemented the WGCNA to create these modules. These are some helper methods that I'll show as I use them. The first step was to calculate the adjacency threshold parameter, the soft threshold. This is a parameter that helps reduce the noise in the calculations. Basically, it's a parameter that sets a value for coefficients. Anything below that value goes to 0 to eliminate those coefficient terms. So there's a function that's provided. This function is provided by the WGCNA package itself. Basically, you pass in the data, it does some calculations, it calculates this R squared value, and we take all that data and we make a nice plot of the results. And the idea being we want to pick a soft threshold value here where you get a peak model fit, a peak R2. I said that this is the peak right here, and I said this is approximately 13. So that's what we're using. I did experiment a little bit with values between 11 and 15, and it really didn't change anything. I think it mostly just helps the calculations. So after we plot that, we start doing the actual WGCNA analysis, creating a network. If we've done it before, we just go ahead and read in that result. Otherwise, here's where we do the actual analysis. So this is our soft power 13 that I mentioned. We're assuming the numbers are signed. And then this is the block size. This is how many genes at a time should be looked at. These are actually the starting value, starting number of genes that are put into a module, and then it's tried to be reduced from there. They recommend a value of around 25,000 based upon the average laptop computer. That's basically what this size is for. It's more of a computational thing. The larger the size, the faster it will complete, but the more CPU speed it will take. Once again, I played around a little bit with the block size. It didn't really change much. So we go ahead and create the network, which means we're trying to see which genes we can group together and see that they are co-expressed together as one group. These are the raw results that are coming through. We go ahead and create the design matrix and a linear model. So each module gets a linear model fit, and then this eBayes is for the standard errors to be reduced. This multiple testing correction is a strategy for adjusting the p-values based upon their relevance to each other. I'm not sure, but it's exactly what's going on. But the idea is to reduce the variance in the p-values by considering them all at one time simultaneously instead of individual values. So after all of that, we get a list of modules and their p-value and their log FC. So these are the overall top 6 modules with the most significance. So they're all significant based upon their p-value. The log FC, the sign of it, tells us whether they're positive or negative expression contributions. So module 4, 31, and 32 are our top 3 positive expression modules, and modules 2, 7, and 29 are the most significant negative expression modules. Here I take the data and I create a data frame so that we can do some math easily. If we want to look at, let's say, ME4, Module 4, and Module 31, Module 4 is our most significant positive module, and Module 31 is the second one. So we just look at Module 4. We get the top 6 genes here and what they are. These are the genes. You'll notice the genes are rather generic. They're not very specific. They're all things related to DNA synthesis and repair. The relationship between them and what they mean we'll look at in the next step, but these are the most significant genes from the most significant module positive expression in module 4. And then this is a plot that just shows, we have the 2 different types of contributions to the modules. Similarly, if we want to look at the negative log FC, so these are positive means more associated with cancer, while negative log FC are those associated with normal tissue. So these genes are more expressed in cancerous tissue versus these genes are more expressed in the normal tissue. Again, we'll look at what they mean here in a few minutes. In the paper, they talk about calculating an adjacency matrix and a topological overlap matrix. They don't really seem to do anything with them. They just state that they calculate them. And I did successfully complete these 2 steps using the provided functions from the WGCNA tool. But these 2 steps take a long amount of time and computational time. So I've just commented them out for now because we don't really use them. So that is the step 4, the WGCNA step. We end up with sets of modules with significant p-values, log FC values, and then each module has sets of genes in them. This next step is just to create the Venn diagram that we want to now. In steps 1, 2, 3, 1, 2, and 3, if you remember previously from the last semester, I was calculating these DEGs, the differentially expressed genes. So now from step 4, instead of DEGs, we were using the modules. We were looking at the genes in terms of modules. And so now I want to see what is the overlap from these 2 sets of results. So I have my module genes and I have my DEGs. We have the positive log FC modules, those associated with tumors. top two were 4 and 31. So I go ahead and do some work here to get all the genes from those modules. I get their names. I go ahead and convert them into their, by default, they're given this long and symbol value. Instead, I just want to use the regular symbol so we can make it easy to read. Gene and gene name, or symbol and gene name. So this is just creating the Venn diagram. I do the same thing here for the negative DEGs and the module negative log FC, those associated with healthy um, tissue. And then here is the actual overlap genes, a list of them that the intersect between the module genes and the DEGs, and I use this term later, but we can look at the Venn diagrams that were created here. I have all these files on the GitHub, but these are the two Venn diagrams. So these are the ones that show the overlap between the DEGs that I found, 1,600 DEGs. There's 300 total module genes between, at least what I'm looking at. I'm only looking at the top two modules by significance, and there's an overlap there of 55 genes. So 55 genes were found, two different methods, 55 genes were found more highly expressed in tumor tissue than in the normal tissue. Similarly here, these are the ones that are more highly expressed in the normal tissue. 2485 DEGs, 610 module genes between these two modules, with 98 of them intersecting. So this is a good confirmation that our results make some sense, because through two different methods, we are getting a relatively large number of intersecting genes. And then now that we have these genes, we can do the gene set enrichment analysis. So now we can do this gene set enrichment analysis. We take the overlapping genes that we found earlier. We do some calculations or some code here to get everything ready to fit into this GSE Go function. These minimum and maximum GS, these I'm not too sure what value to use. I need to do some more experimenting. These are just kind of the default values that I'm using. The P cutoff, again, this is the default cutoff for significance. For the positive ones, I've just set it at that, but if we wanted to change it, you could. And similarly with the negative genes, these are the overlap genes. Again, we're looking at the genes that are the overlap between the first group of work that created the DEGs and the second group of work, the WGCNA, the modules. Again, we're making the negative one here, and now we can do the plot. So these are the first one are the up regulators, the ones that are more associated with tumors. You can see the plot here. So this plot here, the gene ratio is basically the number of genes that, or the number of genes that belong to this term divided by the total number of genes. So basically every gene is related to DNA replication, something very generic. while 70% of the genes are related to double-stranded DNA binding. So what this chart is showing, these are very significant terms, but these are pretty generic results. There's nothing unique here. It's just DNA binding related terms. Again, same thing here with I guess these are the down-regulated genes, the ones that are associated with normal tissue. Again, these are the very significant, good significance, but the processes are not very specific. Biological regulation doesn't tell us anything. Um, but this is the idea. So to get more useful results, I need to spend more time playing around with the various parameters, possibly look at additional modules beyond just the top two. Maybe I need to look at the top five or something else. Try to get some more useful, more specific results. I talked about in the last video the AI tools. I didn't really have time to implement them specifically, but we do have, as I showed in the last video on the website, you can take a list of genes, put it in the website, and it will give you the biological functions associated with those genes. So that is something I need to continue working on. And that's about it as far as this summer's work on this particular project. I do think I've made a lot of good progress. I've been able to reproduce a vast majority of the original paper, if not their actual results, my own version of the results using their methodologies. Um, So I would like to eventually write this up into my own paper just to show what I've done and hopefully try to at least get a conference presentation out of it. So that's probably what I'll end up doing this fall. I am signed up to take a class as well as take the graduate seminar series for this fall. And then in the spring, I'll be taking another class. I'm not sure when I'll be taking thesis credits again. Could be in the fall, in the spring. If not then, it will be in the summer of next year. And that's probably when I will return to thesis work. Probably I will spend my full time then working on things not related to this bladder paper, but my own particular research topic that I hope I'll be able to have narrowed down and identified by then. If we want to meet in the springtime to discuss my progress, we can. I tried to meet last year, but we all ended up waiting to the last minute and there really wasn't time to do it. So if we want to meet to discuss thesis progress, we can in the next springtime. And that is it for my work this summer. I am putting everything onto my GitHub, and if there's any feedback or questions at all, please let me know. I will hopefully be spending this fall writing the paper, getting that submitted, and finishing up my class requirements. So that's the plan. Thank you, everybody.